Now this is the Schwarzschild metric and the Christoffel symbols. The Schwarzschild metric is 4D, spherically symmetric and is vacuum. And the coordinates are here, t, r, theta, phi. Now our element, line element, is this here, whereas as again the signature here, where m is the mass of the central object and c is the speed of light. These components here may look familiar from Newton's laws. That's where they were originally derived from. Now the metric tensor components are given here, and this is the metric for the Schwarzschild metric. Now the inverse metric is here, so we're just basically inverting everything. Now if we see this part here is G, phi, and so on. Now the Christoffel symbols, the formula again is here. We compute the key non-zero symbols. So RTT equals 1/2 G, G R half D theta GTT, where these are the regular component and its inverse, with a partial derivative whacked in between them just for good measure. And after doing that, which it looks complicated, but it really is a simple operation. We're just taking a derivative and just collecting and whatnot, and we will get this. And for our component, our TRTT, we will end up with this. And if we follow through for all the other components, GR, RR, we get this, and GR theta, this, and GR phi, we get this, and similarly, we'll get this. Oh, in fact, I think I've just duplicated that, haven't I? Just ignore the top part, I suppose. G theta, R theta, and gamma theta, R theta, and theta R both equal 1/r. So our Christoffel symbol here is 1/r. And so our Christoffel symbols are given here. Some of our Christoffel symbols, 1/r and cotangent of theta. Our cotangent comes from this, because this is the r squared sine squared theta. You'll see this on any kind of gradient or divergence in spherical polar coordinates, and that's where it comes from. It's just basically we're just taking the derivative here of this with respect to theta, and we will end up with cotangent theta, which is one of our Christoffel symbols. Now Christoffel symbols are used in the geodesic equation. This is our line through curved space-time. So the Christoffel symbols, what we found here, goes into the geodesic equation here, and this gives us our path through curved space-time. Now for radial motion, theta equals pi/2, phi is constant, only r and t components matter. Using our gamma RTT components, we can find the effective gravitational acceleration here. Now for orbital motion, theta and phi components produce angular momentum conservation and explain perihelion precession, like the planet Mercury, which I believe Newton's laws broke down in being able to predict this phenomena with Mercury, but this is where general relativity was effectively sort of proven, came into its own. I think actually general relativity was proven conclusively by light passing the sun from a distant star, and it was shown that light did in fact bend around the gravitational field produced by the sun. But anyway, the summary is that the metric transforms under coordinate change here. The Christoffel symbols computed for metric derivatives encode gravitational forces in curved spacetime. The geodesic equation uses Christoffel symbols to determine motion. Now, Schwarzschild metric yields all classical general relativity phenomena, orbits of planets, light bending, gravitational time dilation, and black hole horizons. Now that's the end of this mini lecture. Please do like and subscribe.